Okay, so the so you have sequences in R. So they're basically a collection of numbers that are ordered, right? So the sequence, actually, the order of the numbers in the list is actually important. Okay, that's why it's called a sequence. They should not be confused with sets. All right, your set is basically just a collection of numbers without any context to the order, all right, of listing the numbers. Okay, for example, you can have two. So this is, for example, if you write 1, 2, 3, 4, 5, this can be a sequence, all right? Well, this is a finite sequence. Or it can also be written as 2, 3, 1, 4, 5, right? So basically, if you treat this as a finite sequence, then the order is important. And therefore, if this is if you consider this as a finite sequence, so this and this will be different, right? But as a set, they will be the same. Okay, so A and B will be the same because the elements there, they are the same. Okay, so when you talk about sets, basically you don't care about the orders, right? But if you talk about sequence, you care about the order of numbers, okay, in the list. Right, okay, so I'm going to give you some examples of sequences and how we write them. Okay, so the simplest one is the sequence of natural numbers. So 1, 2, 3, 4, 5, and so on, right? So you can write as follows. You have a curly bracket, then you have n. This n is the indexing, right? So that means if this is something like a function. If your n, so your n is an element in the set of natural numbers, right? So which is 1, 2, 3, 4, 5. So when you have 1, you have 1, okay? When you have 2, you have 2, and so on. Okay? Remember, you have to have a okay. So basically, this is just describing how the numbers are ordered in this list. Okay. And this one, 2, 4, 6, 8, and so on. This is the sequence of even numbers. All right. So you'll write that as 2n. Okay. Because as you put n equals to 1, you will get 2. N equals to 2, you will get 4. N equals to 3, you'll get 6, and so on. Okay. So these are very simple sequences. And then perhaps maybe something slightly more unusual. So you have the following sequence, which is basically you have 1. So forget about the sign first, right? You got positive, negative, alternating. The point is that you basically have the numbers are actually halved, right? For the next number is the half of the previous one, right? So 1, you halve it, you get 1 over 2. You halve it, you get 1 over 4. You halve it further, you get 1 over 8, and so on and so forth, right? So every number is 1/2 of the previous number, right? And then the positive, negative sign, they alternate, right? Start at positive, negative, positive, negative, positive, negative, and so on. Okay. So we can actually, how should we represent this sequence? You can write it compactly as follows. So since this is, you take a half, right? Okay, so generally you can have 1 over 2, n power of n minus 1 because you start with 1, right? So to get 1 here, you have to have 1 over 2 power of 0. So, okay, that will give you 1. And then you want a sign to be positive. So your control for the sign here is -1 raised to the power of n plus 1. Okay, because when your n is 1, you have 1 plus 1, then you will get 0, okay, which is 1, right? So, and you can try if your n is equal to 2, so you will get 1 over 2. and 2 plus 1, you will get 3. So minus 1 raised to the power of 3 is negative. Okay. Of course, another way to write this would be, you could also write it like this. Okay, this will also work, right? Okay, so is it clear? How you express sequences compactly? All right, okay. So I guess you're okay with the sequence, yeah? Now then,
Yes.
if you look at example 3.4.1, there are some further examples. And I also showed that maybe you can also have a trigonometric sequence, right? So you have cos of k pi, where your k is an element in the set of natural numbers. So this sequence will be very easily like this. So you have k equals to 1. So you have cos pi. Cos pi is, what is cos pi? Minus 1, right? Then you have, because cos 0 is 1, cos pi is minus 1. And then you have 2 cos 2 pi, you will come back to 1. Cos 3 pi, you will go back to minus 1, right? So basically, this is like, okay, it's like an alternating, a sequence of alternating minus 1 and 1. Minus 1, 1, minus 1, 1, and so on. Okay. You could also express this in an equivalent way as follows. Okay, so you have minus 1 as the base, so you raise it to the power of, you can use k. Since I use k, so I just keep k here, right? What should this be? This should be just k. It should be just k because when k is 1 minus 1 raised to the power 1, you get minus 1, right? K equals to 2 minus 1 raised to the power of 2, you get 1, right? So these two representations are the same. Okay. All right. So far so good, yeah. Okay. So now we will come to the important part, which is we want to talk about something called the limit of a sequence. Okay. So if you consider this sequence, which you have the previous number, right? For every number you have currently is 1/2 of the previous number. Okay. If you keep on doing this, right, what will happen towards the end? In the limit, if you keep on taking 1/2, it should tend to what number? Just intuitively, as a feeling, what should the number be?
0.
Okay, 0. Everybody agrees? Everybody agrees that the sequence will converge to 0? Okay. Right. So, okay, it does converge to 0, right? So here, this sequence, we will represent it as 1/2 power of n minus 1, and this, right? So basically, this is our xn. So we say that in the limit, this is equal to 0, right? Okay, and I think intuitively at the more elementary level, people have no problem with this. Okay, they look at the form here, and they know that since this is 1 over 2 power of n, so when the n becomes very large, 2 power of n becomes extremely large. So that's the denominator. And your numerator is a constant. So since your denominator is expanding so quickly, so eventually it will go to 0, right? Now that's the intuitive argument, okay, and that is fine, okay. But in mathematics, as you have seen, intuitions, they can only guide you up to a certain point. You have to come up with some very clear definition of what you mean by sequence converging to some number, all right? So for that, we have the definition 3.4.1. Okay, definition 3.4.1. Now, this is an important one. Okay, so I'm just going to write it out so that we look at it together. We say that a sequence of real numbers okay, xn. So I should have this, but I skipped that in the notes. Converges to some real number, okay? Some real number A, which is some number in the set of real numbers. If and only if for every epsilon greater than 0. This epsilon is some kind of bound. Okay. There exists an n, okay, such that this thing, if this condition is true, okay. This looks like a bit abstract, but basically what happens, if you want to understand this in a layman's term, this is basically just the distance of xn from A, okay, the distance. Xn minus A is of course the difference, right? So you put the absolute, meaning you don't care whether it's on the left hand side or the right hand side, right? Because after you take absolute value, the sign will disappear. So basically it just means the distance, all right? The distance of xn from A cannot exceed epsilon, all right? So if there exists some kind of this means that if n is sufficiently large, then if you have some, this is a threshold value, yeah. So if your index exceeds that value, you are sure that your xn cannot go away from A by more than a certain amount, epsilon. Okay. Now this may not sound very intuitive for you at the beginning. Once you have a good idea of what this means, you can actually, this becomes a very natural definition, and you will appreciate why this kind of definition is actually the correct way to define convergence. All right. So I'm going to give you an example here. Okay, so let me just sketch something. Give me an example. Okay. Let's look at the example of the sequence Change the color. Okay, the sequence 1 over maybe n. Okay, this should work. All right. So what's going to happen is that if I put a line like this, so the first member will start at 1, right? And followed by 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. Okay? So you start with 1 here. Then it goes to 1 over 2, which is here. Okay? 1 over 2. 1 over 3 will be somewhere around maybe here. Okay, 1 over 4 is half of 1 over 2, so it's here. And you have 1 over 5, which is 1 part, so it will be somewhere around here. And then 1 over 6 is half of 1 over 3, so that will be somewhere around here, and so on, right? So it will kind of start to get denser and denser towards 0, right? Okay. Now, suppose you set your epsilon. You set your epsilon to be 3 over 4, right? That means the distance from the limit, here the limit, you're postulating that the limit is actually 0. Okay, so you have to set your A, yeah? So you postulate it to be 0. So it goes all the way until 3 over 4, which is here. Okay. All right. Now, if you take 1, right? If you take 1, the distance from 1 to 0 is 1, right? It is outside of this bound, isn't it? So 1 doesn't work, all right? Now, but once you go to 2, when your n is equal to 2, you have 1 over 2, right? So 1 over 2, the distance from 1 over 2 to 0 is bounded, is definitely less than 3 over 4, right? So you have already found, so for L epsilon equals to 3 over 4, you just need to take n equals to 2. Because from n equals to 2 onwards, right? So that means this guy, the distance is bounded by 3 over 4. The distance from 1 over 2 to 0 is definitely less than 3 over 4, and definitely for the rest as well. Okay? So for one particular epsilon, you find a particular value of n here. This is some number in the set of natural numbers. So as long as you can find a threshold for which all your subsequent values, right? They have a distance that's smaller than the epsilon. Okay, then you are fine. Okay. Now the problem is that your epsilon, right? It just says that epsilon greater than 0. Okay. So it basically can be anything, right? So for example, if you fix your epsilon to be maybe like here. So this is 0.4, let's say. If you fix your epsilon to be 0.4, then your n will have to be larger than or equals to what? Starting from which n? The distance of your xn will be bounded by 0.4. 3, right? It's clear, right? Okay, if you set here, then you have to start taking this. How about if you set your epsilon to be 0.22? So that will be here. If you set your epsilon to be here, so your n will need to be larger than or equals to 5. Okay, that's good. So you can keep on doing this. So basically, since your epsilon can be arbitrarily small, right? It just needs to be larger than 0, all right? So it can be something like 0.0000001. That doesn't matter. It can go arbitrarily close to 0, right? The point is that it doesn't matter how you set your epsilon. You can set it to something like very small. As long as you can find some n, right? You can find a threshold such that for all the subsequent numbers exceeding this threshold, they will be bounded by this value that you set. Then you can be sure that towards the end, your sequence will converge to that particular value. Okay, because the point is that you can set any arbitrarily small number here. Doesn't matter. We don't have to explicitly set any numbers here. It's just a concept, right? So the point is, as long as you can find some threshold here such that when your sequence of numbers exceeds that threshold number and their distance from the A will be bounded by epsilon, no matter how small, then you have succeeded in showing convergence. Okay, so basically, if we say convergence, right, you are saying that the xn, right, gets arbitrarily close to A, right, which A equals to 0 in this case, right? They just get arbitrarily close to A. Okay. So let's see how we actually argue this analytically. So in example 3.4.2, clear this, yeah. The sequence converges to 0, yeah. So we write limit equals to 0. Okay. Now how do you argue in this case? So we need to show, right, that xn subtract A. So this is the distance from A, right? The converged value, right? It's bounded by epsilon, right? For all for every epsilon greater than 0. Okay. All right. So and we can find some n greater than the threshold. Okay. Such that this will be true, right? So so over here our xn is 1 over n and our A is 0, right? So basically the condition that we want to establish is that 1 over n subtract 0 less than epsilon, okay? Right? And since your n is always positive, right? So basically this absolute, you can remove it. So the condition that we want is 1 over n less than epsilon, okay? So this is the distance, right? You need to find some n. You need to find some n exceeding some threshold such that this inequality is true, okay? Now the simplest way to do that is the following. So 1 over n is less than or equals to 1 over big N, right? So this is your threshold, okay? If you can find 1 over n is less than or equals to 1 over the threshold, and this one is still bounded with epsilon, then it will work. Okay, so basically, and this condition here is actually just n greater than small n greater than big N, right? Because it just satisfies this condition. Okay, so so basically you have this inequality, And therefore you connect this part here. Once you build this inequality, you connect this part. And you basically just need to solve this so your n is greater than 1 over epsilon. Okay, which means if you pick epsilon equals to 0.01, then your n has to be some value that is let's say so greater than 100, right? So you can take so if your n is equal to maybe 101, all right, then it would have been less than epsilon. Actually, you can check this. So if your epsilon is 0.01, 1 over 101 is less than 0.01, right? Agree? Because basically this is just 1 over 100, right? So 1 over 101 is less than 1 over 100, which basically is saying that if you have this sequence of numbers, right, up to here at 101 and so on, right? So these beginning ones, their distance from 0 will be larger than 1 over 100. Okay, if you set your epsilon to be 1 over 100. But starting from this tail onwards, their distance to the A will be less than your epsilon value, okay? And it goes on so on and so forth, right? If you set your epsilon to be some very small number, it basically just means that you will cross out all these terms that are in the beginning, and you can still find some number towards the end here, where this where they will be within this the difference of these numbers here from A will be less than the epsilon. Okay, so these guys will exceed. Okay, but it doesn't matter as long as you can find some cutoff in your sequence such that the tail here, they get arbitrarily close to A, then you manage to show convergence. All right. So basically, for this kind of proof, you just need to establish one condition, which is your threshold, right? Depends on epsilon. So as long as you can find that your threshold exceeds some kind of function of epsilon, it's done already. All right. So I give you another example in 3.4.3. 3.4.3, so you have this sequence, 2 plus n over 5 plus n. All right. Okay. Show that the this converges to 1. Okay. Actually, this is intuitively, if you look at this thing, this function here, it definitely converges to 1 because when n is large, right? So your 2 plus n will be roughly n, and 5 plus n will also be roughly n, right? So this will be roughly n over n, so it's 1, roughly 1, right? So intuitively you know this. So let's see how to do it formally, okay? So formally, then we want to have 2 plus n over 5 plus n. This is my xn. I want to find its distance from the limit, which is 1. And I want to bound it within epsilon, all right? So here you can simplify the left-hand side. So you will get 5 plus n, 2 plus n minus 5 plus n, right? Okay, this is the left-hand side, okay? So this will give you, the n will cancel, so you have minus 3 over 5 plus n. which is basically only just 3 over 5 plus n, right? So therefore, this means that, so this implies that you have this inequality. Okay. All right. So you want to find some threshold n, right? Such that when your n exceeds this threshold, this inequality will be true. The easiest way to do that is just the following. So this function here is bounded by 3 over 5 plus n. Just have a complete match here. Okay. And therefore, and then this one, you set the condition that this has to be bounded by epsilon, right? So once you have this, then you just focus on solving for this part. So here it will be clear that your 3 over epsilon is less than 5 plus n. Therefore, your n has to be larger than 3 over epsilon minus 5. Okay. So you set some n that is you take your threshold to be something like this. So what this threshold should be will depend on epsilon, right? If your epsilon is very small, then this n is very large. Okay, and vice versa. Now, many people might think that there's actually a unique solution. No, there's no. Sometimes there are several possible ways to do this, right? The point is that you just need to find in your sequence, right? You just need to find some cutoff such that the sequence of numbers at the beginning, they do not fulfill this inequality, right? That means their distance, they are actually like exceeding epsilon. So we don't want these guys, okay? If you can find some cutoff here, all right, such that these guys, they fulfill this, right? Their distance from A is within epsilon, then you are done already, right? Whether you use, so as long as, okay, it may actually start from here, all right? Your n may actually start from here. And starting from here, these guys are all like fulfilling this inequality. But you do not have to always start here. As long as you can show that after some other value, okay, these are all fulfilling, it's also okay. Okay, if you leave out some of these guys here, it doesn't matter, right? The important part is the tail here. Okay, because of this, you can actually make simplifications to your inequality here as follows. All right, so for example, over here, if you feel like this part is a little bit not so elegant, okay, you can actually further do a kind of simplification here. So I'm going to erase this. Okay, you ask yourself, you create another inequality here that will simplify the form. Okay, so what would this be? This would be less than 3 over 5, 3 over n, right? This is definitely bounded by 3 over 5 plus n is definitely less than 3 over n because you got an extra 5 here. And this doesn't have an extra 5, right, in the denominator. So definitely this is less than this. The left-hand side is less than the right-hand side. And this, of course, you can set the condition to be less than epsilon, right? And then you focus on solving this part. And this will basically give you a simple solution, which is n larger than 3 over epsilon. Okay? All right, so this will also work, yeah? So either you can give this solution or you give this solution. It is okay. So this solution is like you take everything, okay? Because 3 over epsilon minus 5, that means you are taking something that is like more. Whereas this one, you are basically just taking something towards the tail. But it doesn't matter. It's actually the tail behavior that is important. All right. So this trick can be quite useful. Like when you first construct the inequality, sometimes this part may be, if you want to solve directly like this, okay, this is still okay, but sometimes this may be complicated. So when you try to solve this, it may be a bit tedious. So you may actually consider simplifying this inequality first before you solve. Right. Okay. Okay. Is it clear to everyone?
Yes, clear, Doctor.
Okay. This is actually if you know how to do this, right, your it will sharpen your appreciation of the concept of convergence later, yeah, because later when you study probability theory, there are a lot of convergence results. So we need to first sharpen our understanding of what convergence means in a technical sense. All right. Okay. So there are sequences that converge, but there are also sequences that don't converge. Okay. So I give you an example. So the example is the alternating sequence, yeah, this sequence. Because this sequence basically is just -1, 1, -1, 1, -1, 1, okay. So it's like flipping between -1 and 1, -1 and 1 and so on. It doesn't settle to any particular value. This is what we call an oscillating sequence. Oscillating. Okay, because it's basically moving like without setting at any particular value. So you want to prove that this does not have a limit. It doesn't converge, right? It doesn't converge. Okay, so if you read the proof there, right? The proof is by contradiction. Okay, by now you have seen that there actually are quite a lot of proof approach in mathematics that uses the strategy of contradiction. Okay, this is a repeatedly used. This is a very useful strategy in proofs. That's why we keep seeing it coming up. Proof by contradiction. So you want to establish a contradiction. So you will assume that A exists. You want to prove that A does not exist. So you prove by contradiction by assuming that it exists, and then show that this assumption leads you to get some absurd conclusion. Okay, so then you establish a contradiction. So if A exists, then what will happen? Then you will have this, right? Okay, then you have to work with this inequality. Okay, now then you consider the two cases, odd n, right? Because your n can be odd and even. When you have odd n, you will have -1 minus A less than epsilon, right? When you have even n, you will have positive, so you have 1 minus A less than epsilon. Okay, so this is the same as this implies 1 plus A less than epsilon, all right? Because you can take out you can factorize, and then the minus becomes positive, right? So this actually implies this. Okay, so we have got these two inequalities that are implied if you assume convergence. Okay, now once you have this, look at it carefully. I can say I know that 2, right, is equal to 1 plus 1, right? And I can put the absolute sign. Okay. Okay, no one will dispute this representation. Now, watch what happens next. Okay, you want to connect this statement here to these two results that you have here. So the simplest one is to, and you can see that there's a minus, there's a plus. So you have 1 minus A plus 1 plus A, right? Okay, you are not doing anything illegal here, right? Because you are basically introducing a term minus A and then you're canceling it off, right? The interesting part here is that once you have this form, okay, you can think of this as one part and this is one part. Then you can apply the triangular inequality. Okay, the triangular inequality, which states the following. The triangular inequality. A plus B is bounded by A. Okay, if you have A plus B, take the absolute, is bounded by the absolute of A plus absolute of B. Okay, this is called the triangular inequality, which is a very useful inequality in analysis. Okay, so basically now you are saying that, okay, all right, okay. So here you will choose, it doesn't matter. You can choose epsilon to be 1 or something else, because the point is that as long as you can demonstrate a contradiction for any particular epsilon, you are done already. Okay. So for this purpose, you choose epsilon equals to 1. All right. So this becomes 1. Okay. Because if the limit exists, right, it should hold for all possible epsilon. Therefore, if you can show even one case where this is not true, then you establish your contradiction. Okay. Now, so if you set it to be 1 to make it easy, so then this will be so you know that 1 plus A is less than 1. So this will be what do you have? 1 minus A plus 1 plus A will be less than 2, right? Because 1 minus A is less than 1. So here, and 1 plus A absolute is less than 1, right? So when you add these two together on the left-hand side, on the right-hand side, you add together. So you get 2, yeah? So the inequality sign will hold, okay? So what happens is that you will get less than 2. And the statement that connects the left to the right is that you have 2 less than 2. Okay? Which is an absurdity, right? 2 is 2, right? 2 cannot be less than itself, isn't it? So you manage to derive the contradiction, and therefore the proof is complete. Yeah, the assumption that the limit exists is false, and therefore the contrary is true. Yeah, the limit does not exist. Okay. So you can think about this again. All right. Think about this argument again. It may take a bit of time for you to appreciate it, right? But basically the idea is to derive a contradiction, and over here, because you have these two inequalities here, the trick is to notice that, introduce that, and make use of the triangle inequality. Okay. Okay. So that's all I want to talk about the sequences. And so I've released the tutorial 1. So let me show you tutorial 1. Tutorial 1. Okay, let me see. Tutorial 1. All over the place. Okay, should be this one. Okay. Can you see the tutorial 1 page?
Yes, doctor.
So there are 7 questions here. You're covering the material up to today, yeah. So you can try this. You have to try these problems, yeah. Problem 1, infimum and supremum of sets. Then countable sets, right? Image and inverse, algebra of sets. Then the limits, right? Limits I have 3 examples. Okay. Okay. So can we decide who would want to present these questions? Just look at the questions a bit, and then you can volunteer yourself. Yeah. Okay, Suta wants to try problem 3. Suta, okay. Om wants to try problem 1. Sitino Omaira wants question 6. Hajali wants to try 7. Dina 5. Atira Nudra 2. Four is actually rather simple, so they don't get tricked by the notations there. This is basically set operations, but you are doing a lot of multiple operations, right? Okay, Aida Maisara, okay? Okay, great. So So for next week, yeah, next week we start to have tutorial from 11 to 12. From 12 to 1, right? So you should how should we do this? So you should maybe write it down, right? Your solution on a piece of paper, or if you want to type it out also can. You scan it, convert it to a PDF, and during the e-session, you just share screen and talk about it. Okay.
Okay, Doctor.
Was it Hajar who told me that you have something?
Yes, Doctor. From 12:30 plus minus to 12:45.
Oh, okay. So maybe we let you have a go first, lah.
Okay, sure, Doctor. Thanks.
Okay. So we might start with problem 7 first. All right.
All right.
Okay. Okay. So that's all for today's session. Please make sure you sign the attendance here in Spectrum. Okay.
Okay, thank you, Doctor.
Okay, thank you, everyone. So I'm going to stop the recording now.